All right, so let's get started here. This video is intended to give you all some intuition about parametric surfaces, how to build them, what they mean, how to interpret the equations, and really just how to think about this. So we're going to start with a pretty simple surface, and that is a cylinder. And we're going to go ahead and learn how to derive the surface parameterization. Now, for this video, I did want to have visible all of these equations here, just so we can see them. Not all of them are we going to talk about in depth. Some of them are just to do an animation later, but really our goal is to figure out how can we parameterize this cylinder. So let's go ahead and look at a blank graph, and hopefully we can arrive at this, arrive at that. So let's go ahead and think about how we might build a cylinder. So here we are in the, I went ahead and graphed a circle in the XY plane. It's the unit circle. So over here is our basic one-dimensional parameterization that we're used to. R of t, or whatever you want to call it. So this is our one-dimensional path parameterization. It's tracing a path. I can go ahead and toss some orientation arrows on here so that we can see exactly the orientation. And we can even trace it to see what's going on here. So I'm going to go ahead and I'm going to take off the acceleration velocity vector just so you can see the trace point is all I want to see right now. Okay, and we're going to bounce over the range. Okay, let's try that. So if we animate here, it goes all the way around, and that did tell me I actually wanted to turn that off. Okay, there we go. Let's try that now. So this is just going to go around and around and around. 0 to 2 pi, again and again and again. So you can see that we start off here where we usually do along the x-axis, and then we work counterclockwise towards the positive y-axis, and that's how we trace that circle. Now, if we look at the cylinder in the other calc plot 3D, you can see that the maximum the cylinder extends to is a height of 4, and if we tilt down a little bit, we can see there's a 2 in there. So this is a cylinder that begins at a z-value of 2 and stretches to a z-value of 4. So really, at the very least, this circle shouldn't be in the xy plane. It would be useful to have it lifted up too. So we know how to do that. We can just change the z-value from being 0 to 2. Now that circle, if we were to trace it, it lives in that plane. Z equals 2. So that's good. But here's the thing. We don't want to just think about tracing this circle at a height of z equals 2. We want to trace it at every single height between 2 and 4. Every single height. So the way I would think about this is if you were to watch a cylinder being printed, like 3D printed, or being constructed using some sort of mechanism like a 3D printer, what would happen is the printer would start, you would heat up the filament, and then it would print out the filament starting at a point, and then the printer head would actually rotate, printing out that filament until it does one full rotation. Once it gets to this, once it returns back to its starting point, what will happen is we can think of the height increasing. Maybe I'll go ahead and say the height increases to 2.2. So it moves up a little bit. Maybe the thickness of the filament is, I don't know, 2 centimeters, or not 2 centimeters, but 2 millimeters or something like that. So then it moves up a little bit, the thickness of that filament, and then again we can think about the printer head rotating and getting back to its starting location. And then we rinse and repeat. This goes from 2.2 up another 2 millimeters. And then the printer head yet again rotates. And if we visualize this, we just see the printer head going around and around and around while it moves upward. So if we were to visualize this, perhaps maybe instead of me manually changing it from 2.4 to 2.6 to 2.8, so on and so forth, how about in CalcPlot, we just hit A, and then that will give us the slider that we can now change the value of it. So let's make A go from 2 to 4. And we can do it in steps of maybe, let's just do 0.2. Or, sorry, let's just do 100, make that easier. All right. So then you can see that if we animate A, this is going to move it up and down in the Z direction from 2 to 4. All right, so if we were to watch this in real time, the printer head might do something like this. Let's imagine it starts lifting up, and then the printer head would rotate around and around, tracing circles or printing little circles of filament, little rings, and stacking the rings effectively. The printer head will move upward from Z equals 2 to Z equals 4. And the printer head the entire time just rotates. That will go ahead and print the full cylinder. And that's exactly how I visualize and how I think about parameterizations. I think of it as instructions for how to create or draw something, sort of procedural drawing. How do you draw a cylinder? Well, start by drawing a circle, and then just lift that circle at every single height, draw another circle. That's exactly what's going on here. So as you can see here, we really, in order to get the cylinder, we needed a variable for here, for t, so inside of cosine and sine, we needed something because that's what was actually allowing this to go around. I can probably make that a little bit slower now. So we need a variable for the angle, or else we won't go around the circle. And we also needed another variable. We created a slider in CalcPlot 3D, but this really does, we needed this value to change. We needed to lift this up and draw a circle at every height. So the very fact that we have these two different moving pieces tells us that in order to draw a cylinder, we're going to need a parameterization of two variables. So if we go to the select, and I don't know why this doesn't pick up on the video, but there's an option called Parametric Surface, and if I click that, I get this. So let's go ahead and just turn this off for now, the circle. And let's go ahead and notice here that we had cosine of something. We had sine of a variable. And here we had another variable. Well, here, our only variables that we can use up here are u and v, or we can also add a slider if we wanted to. But the whole point of going from a parameterization of one variable to a parameterization of two variables is the fact that we want there to be two variables here, because we needed, in addition to t, we needed the a. So now that we have access to two variables, we don't need this a anymore. We can get rid of that. So instead, we'll have cosine of, let's just pick one of the variables. Let's just say u. And since t appeared both in cosine and sine, well, it's the same variable. That's our angle parameter. So cosine of u and sine of u, and we would want to make sure we edit this to say that it goes all the way around the circle, and this just so happens to default to 0 to 2 pi, so that worked out nicely. And now what's going to happen here? Well, we don't need a slider anymore because we do have access to this second variable, so we can just make this v. Now v is going from a value of 0 to pi. And since v only appears here in the z component, this is saying that effectively we'll get circles being drawn, starting with a circle at a height of z equals 0 and ending at a height of z equals pi. So we want to actually change this to 2 to 4. And there we go. There is our cylinder. And that's the same exact cylinder that we have over here. Okay. This has some additional grid lines. There's more samples on this one over here. That's why it looks a little bit coarser on this side. I have a different number of samples. All right, so here's our cylinder that we just created. And here you can see there's our same surface parameterization, cosine u, sine u, v. So now let's go ahead and visualize. If we click down here and we look and we see the u, this should be u, I don't know why that's doing that. That should be 0 to 2 pi. And that should be 2 to 4. Okay. It's very strange. Don't know why that happened. Okay. So let's go ahead and turn all of that off. Oh, sorry, that one we'll leave on. I do not know why that did that. Okay, those all look fine. All right, so there we have our cylinder. And now let's look at our range here. We have u between 0 and 2 pi, and we have v between 0 and 2. What we could do is actually think about drawing this range of u and v in the xy plane. Now I know that this is the xy plane, and this is the x-axis and the y-axis, and x and y are different than u and v, but for the purpose of this video, let's just pretend that this is the uv plane, okay? So what we're going to go ahead and do here is I'm going to turn on a portion here, a portion of the plane, and we can see that if we're going to momentarily pretend that the horizontal axis coincides with the u-axis, then we definitely have 0 to 2 pi. Remember, 2 pi is about 6.28, so that definitely works out for the u-axis. And for the range of v, 2 to 4, we get this. So here we see this little rectangular portion of the uv plane. And now what we can imagine here is our parameterization that we built down here, that if we think about the domain space, so this is the parameter domain. So right here, this yellow rectangular strip, this subset of the UV plane is the parameter domain. So U goes from 0 to 2 pi, V goes from 2 to 4. This shows us a way that we can actually visualize taking this region here and morphing it into this region here. So to do that, what we can think about is, let's actually think about animating this. So I'm going to go ahead and turn my slide as my animation slider. And here is the thing I need for the animation. So if I click animate now, we'll see that the portion of the plane down here will get up and move, bend and roll, and then we'll tape the ends together. So that visually is kind of what we're thinking about. So it's very interesting that the idea of drawing stacking circles and drawing a circle and moving upward gives us the same result as if we had a strip of paper, how we could tape the ends together. The two notions coincide, which is very interesting that we see that. All right, so there's another thing I'm going to talk about for a moment here, and that's called the grid curves. So something that we'll talk about in depth is grid curves. So a grid curve is, for instance, in the UV plane, so this domain right here, if I set u is equal to a constant, so let's say here we let u equal a constant, so let's go ahead and say something like, pardon me, let's turn my animation down. There we go. Make that right there. Okay, so in that case, let's try that again. Here we are. So I went ahead and enabled this one. And what this effectively is if we let u equal a constant, well, if this is the u-axis, again, we're just pretending that this is the UV plane. So if this is the u-axis, the horizontal, then if we fix u to be some value, so I don't have access to the, if I say u equals b, so right here, then I can see that if I move b, I really am just getting a vertical line. And that's what it does look like, right? If this were the x-axis, x equals 4 is just a vertical line through x equals 4. So if this is the u-axis, then u equals some number b, let's say 2, then we just get a vertical line through u equals 2. All right, so now what we want to think about is what happens to this line when we morph it, this rectangular strip, we morph it onto that cylinder. So if we go ahead and do that, we can watch what's happening to it. And that vertical line, oop, looks like we're going to lose sight of it, so let's rotate. Where's it going? There we are. So what ends up happening is vertical lines in this plane, they get mapped or morphed into vertical strips on the cylinder. Similarly, if we think about doing the opposite, what if instead of considering a vertical line, u equals a constant, what if we consider v equals a constant? Well, that would look something like what I have in red here. If I turn this on, and then this is, let's say v equals a constant c. So if I change my value c, I move up and down in here. So what happens if we visualize the animation? Oop. Let's start back here. Looks like that gets turned into a circle. So the grid curves are essentially, what do horizontal and vertical lines in your parameter domain, what do they get mapped or turned into upon passing through this parameterization? So if we think about morphing a horizontal and vertical line, what do they get turned into? Well, if we look at it all at once, and let's move my green arrow, or my green one right to the end here so that we can see it on this face. So if we animate it, horizontal lines, the red line, turns into a circle. And again, a little bit hard to see. Maybe I can move my green around a little bit. There we go. We end up getting vertical lines. So a vertical line still is vertical, but it's now in the z direction extending. Horizontal lines in the UV plane get wrapped into circles. So this green line and this red circle on the surface of the cylinder, that is what a grid curve is. In fact, these two things actually create a natural coordinate system, so to speak, on the surface. We'll use these curves later on when we do vector surface integrals.